All right, let's look at the molecular geometries based on 5 electron domains. So I'm going to start off just with our base geometry. 5 things. We have 5 bonding domains, no lone pairs. Well, whenever we have 0 lone pairs, the molecular geometry is going to match the electron domain geometry. They're the same. So 5 domains gives us a geometry that is called trigonal, triangle, bipyramidal, or bipyramidal. Why again? Because we have a pyramid on the top and we have a pyramid on the bottom, all with an angle, or all of those have a triangle base. Now, the interesting thing about this particular one, more than any other thing, is that it has 2 different bonding angles. That is going to play a role in figuring out the molecular geometries here. We have an angle from the top atom to the ring around the middle, or the bottom atom to the ring around the middle. Those atoms on the top or the bottom are called the axial positions. So top or bottom to a ring around the middle, imagine this as a wheel. This is like the axle that you would turn the wheel, or the axis of rotation here. So those are our axial positions, and that angle is 90 degrees. In the middle, you have a ring that's split 3 ways. So those have angles of 120 degrees. I'm going to draw that right here. So where do you put the lone pairs? Remember, lone pairs need a lot of room. If you put them on the axial positions, top or bottom, those lone pairs are going to be 90 degrees to 3 other atoms. Okay, can we do better? If we put them in the middle positions have a name as well. They are called the equatorial positions, the ring around the equator. If you put them in the equatorial positions, they are only 90 degrees to 2 atoms. That's where you want to put them. You always want to stick your lone pairs for this structure in the roomy equatorial position. So let's go through the different geometries where we put lone pairs on the roomy equatorial positions. So let's go ahead and start out with beginning structure. If we have 5 bonds and 0 lone pairs, then the geometry matches the electron domain geometry, and we call that trigonal bipyramidal. Trigonal bipyramidal. Okay, now let's go through variations where we have lone pairs. Let's say we have 4 bonds, but one of them is a lone pair. So still 5 electron domain geometry, still 1 up, 1 down, 3 in a ring around the middle. But where do we put that lone pair? We always put the lone pair in the roomy equatorial position. So I am going to go ahead and ghost out one of those lone pairs. Now, what do I see? What I see is the molecular shape. What I see looks like, if I turn it on its side, a childhood playground toy that lots of people used to get hurt on. A teeter-totter, or a different name for a teeter-totter, we call it seesaw. This is a seesaw geometry. All right, so let's go ahead and try another lone pair. What if we have still 5 domains, but 3 of those are bonds and 2 of those happen to be lone pairs? Okay, if we have a choice on this particular one of where to put the lone pair, put the lone pair in the roomy equatorial position. We've got 2 of them. This time I'm going to draw 1 ghost here and 1 ghost here. Pretend like you can't see them. They're ghosted out. Now what you have left over is a letter. If you look on its side, this is the letter T, and they call it T-shape. Okay, there's your next one. Now let's go for the very next derivation of this. Let's say that what you have, I'm just going to do this one right in the middle. Still 5 domains, but this time 2 of those are bonds and 3 of those are lone pairs. So where do you put the lone pairs? The roomy equatorial position. So we're going to ghost out 3 of those. I'm going to make a lone pair ghost here, a lone pair ghost here, a lone pair ghost here. What I have left over is 1, 2, 3 atoms. Those 3 atoms are all in a line, and therefore we call it linear. All right, so those are our variations on 5. Join me in the video below and we'll go ahead and do variations on 6.